I'm very excited to be presenting on investment incentives in near optimal mechanisms. This is joint work with Mohammad Akbarpour, Shengwu Li, and Paul Milgrom. And it's being recorded on June 25th, which, as you will see in a few minutes, is an auspicious day for this talk. I don't actually know which day it's airing, so we're tacking to the recording date. But what's today's paper about? It's about the long-run implications of market clearing mechanisms, sort of crossed with the economic implications of approximation algorithms. We're sort of thinking about how do the systems we use to clear the market change participants' incentives. In this case, in particular, is going to be to invest, sort of in resources or sort of complementary goods and services before they participate in the market clearing process. And I had that little time symbol, but we'll see very soon that like the real hero of the day is going to be, sort of an X, made of bones, and we'll see why. All right, very good. So a little bit more color on the setup. So we're going to be studying a setting in which market participants make incentives prior to participating in a market clearing process. So it's mechanism design with ex-ante investment. And this happens in many, many different contexts. One in particular that's near and dear to, my and especially some of my co-authors' hearts. You might imagine that a TV station is going to be bidding in a spectrum auction. But of course, if you're going to buy spectrum, you have to invest in equipment and television programming and so forth. And you actually have to make a lot of those investments before you show up because they determine your value for winning the auction, right? If you can get really good programming, then maybe you have a much higher value for winning. It's well known that fully efficient investment is a characterizing feature of VCG in the sense that VCG has this property. So it fully incentivizes participants to take the socially efficient investments before market clearing. And also, in some sense, it's the only mechanism that does that. But of course, in this community, we know that in many real problems, exact optimization is impossible. And in particular, in that spectrum context I just described, our co-author Paul Milgrom was heavily involved in the design of the incentive auction that recovered spectrum from broadcasters to sell to telecoms. And dealing with this problem, there's sort of these like very, very complicated combinatorial interference constraints, and figuring out even which packings of broadcasters were possible involved solving an NP-hard problem, and they had to do this lots of times. So you can't necessarily compute the fully optimal allocation, but we have many approximately efficient allocation rules instead. And in fact, there's been sort of huge amounts of work on that in this community for years. So what we ask today is sort of what are the economic consequences of using an approximate allocation rule? When do the associated mechanisms guarantee approximately efficient investment? A slightly more formal version of that statement, and we'll be very formal in a moment. If a bidder knows her price in a strategy-proof, approximately optimal mechanism, will she make approximately optimal investment decisions? And the answer is going to be this X bone I hinted at before. No, in general. So in general, even an arbitrarily good approximate allocation rule can lead to arbitrarily bad investment incentives. But under a condition that we call X-bone, the allocation guarantees push through to investment guarantees. So if you exclude bossy negative externalities, then indeed you get a really strong investment guarantee out of a strong allocative guarantee. This is going to cover a number of common approximation algorithms that we use in practice, including greedy and M-greedy, but it's not going to cover the FP-TAS. So I mentioned this is an auspicious day for the recording. It happens to be what would have been, he just passed away recently, but it would have been Eric Carle's birthday today. And not only does Eric Carle, sort of have the initials EC, but he wrote this book called A House for Hermit Crab that is really about this paper. So to just remember the intuition about the paper, what happens in this book? So we have this hermit crab who, goes around the ocean floor, making all of these investments in improving the quality of his shell. So he gets like very decorated. He sort of meets all these different friends and decorates his shell, but then he outgrows his shell and he has to give it away to another hermit crab because he doesn't fit it anymore. But of course, how does he do this? He applies the greedy algorithm. So the first hermit crab he sees is the one he gives the shell to. And so the question is, if the hermit crab knows he's going to outgrow his shell and like use this greedy allocation rule, what does that do to his incentive to decorate his shell properly? In this paper, we're going to show that there's sort of like, the efficiency of his investment incentive exactly maps to the efficiency of this sort of like ocean floor greedy discovery process. All right, very good. So here's our model. We have a set n of bidders. An allocation instance is going to be a pair V and A. V here is a value profile, so a value for each of the bidders, and A is a set of feasible allocations. Allocation problems collect together a set of instances, and an allocation algorithm for every individual, for every individual problem gives you a chosen feasible allocation. Right? So, there's a map from problems for every instance gives you a feasible allocation. We're going to assume for technical reasons that each bidder's valuation space is convex in each instance. And this is going to capture lots of, approximation algorithm settings we know and love, / have to use in practice. So for example, a knapsack problem can be written in this form, right? Knapsack, you have a set of feasible subsets. That's your, sort of set of feasible allocations. And so your instance is just going to sort of ask, what's the optimum given the feasibility constraints and everyone's values. Cool. All right, a little bit more notation. Welfare at a at a given instance is just going to be the sum of all the values of the bidders who we think of as packed. So every everyone who's in the eventually selected allocation, we're going to add up their values. That's welfare. And optimal welfare, of course, is that at the maximum. Again, we're not necessarily assuming we know how to compute or achieve that, but that's going to be optimal welfare. And then a mechanism pairs an algorithm with a payment rule. So an algorithm is monotone if for any bidder who is packed, so if you are part of the selected allocation, and I raise your value, you remain part of the allocation, right? So standard monotonicity condition. And it's also well known that monotonicity lets us define a threshold auction. So a pricing rule associated to the algorithm that says, we're going to sort of pay you the threshold price that determines whether you are or are not packed, right? So holding everybody else's valuation fixed, what's the lowest price that would, or the lowest value rather, that would cause you to be packed, we'll call that your price and charge you nothing otherwise. So some just baseline sort of interpretation of what that means. For the optimal algorithm, the corresponding threshold auction, we all know and love it, it's VCG. More broadly, if I give you a monotone algorithm, then the associated threshold auction is going to be strategy proof. And in some sense, and sort of like, morally, that's an if and only if, right? So if I give you a strategy proof allocation mechanism, then, sort of it turns into something that is a threshold auction, with this like additional Grovesy component, right? That potentially, you might, change the levels of payments in a way that doesn't depend on your individual value. So really, it's like these monotone threshold auctions are sort of our exhaustive set of ways of making algorithms strategy proof. So that's all standard, right? That was like that's the classic model. What we're adding in is this investment component. So now we're going to imagine that before you show up to participate in the mechanism, you're actually going to choose your value by making an investment. So you choose an investment, VC from a finite set, and C is going to be your cost of making the investment. V is going to be your valuation. And we're thinking about a model in which one bidder makes an investment, everyone else's sort of valuations are fixed. So like in the paper, we talk a little bit about what happens with multiple bidders, but we sort of already know that with multiple bidders, there are coordination failures and investment and so forth. Like we're focusing just on like, what are the implications for a single bidder? So you're going to choose your investment. You're then going to face one of these threshold auctions, and you're going to choose your investment to maximize your payoff given the valuations of the other agents. The mechanism, we're going to say, has efficient investments if you're always incentivized to make precisely the socially efficient investment. And it's well known that any VCG auction has this property. And moreover, it turns out that VCG is essentially the only such mechanism. So if you want fully efficient investments, you're sort of tied to something that it looks, more or less like VCG. So we naturally move to approximately efficient investments. So we're going to relax to approximate allocation mechanisms. So this is, standard concept. You need to be within a fraction beta of the optimum. Here's your welfare. There's the optimal welfare times beta. And we're to say that an algorithm is a beta approximation for investment if we have the same property with respect to the investment choices. So the socially efficient investment is going to be over here. So this is optimal welfare at the socially efficient investment and the cost associated with the socially efficient investment. We need your actually chosen investment to always be within a beta fraction of that. So question is, suppose X is a beta approximation for allocation. When is X going to be a beta approximation for investment? Of course, the natural hope is that the answer is always, but unfortunately that turns out to not be true. So for any beta less than 1, so for any chosen beta, including getting very close to sort of perfectly efficient allocation, there's a problem in a monotone algorithm with a beta guarantee, but no strictly positive investment guarantee. So you can get, arbitrarily close to fully efficient allocation with arbitrarily bad investments. So near optimal allocation doesn't imply near optimal investments. And the question is why? So there's actually like an intuitive reason, which we were surprised to realize this, but ex post is actually really intuitive, which is that there's essentially an algorithmic externality. So under VCG, when I change my investment, if this changes anybody else's allocation, I immediately pay the cost. Right? In VCG, you sort of fully internalize the impact of your change in valuation on other people's changes and outcomes. But here, in approximation space, I can sort of move us into a worse part of the approximation space, which lowers the value for other bidders without affecting my price. So if I, change my value, it might cause the approximation algorithm. Remember, there's beta of slack. Maybe we were really close to optimal. I change my valuation, it moves us to just barely at that beta bound, which hurts everybody else without affecting, or it can hurt everybody else without affecting me. And so there's like an externality through the approximation of the algorithm. And of course, because it's an externality, I'm not going to think about it when choosing my investments, right? Unless it actually changes my threshold price and whether I get packed. And so this was sort of really surprising to us to realize that like algorithms, sort of the approximations themselves can have these sorts of internal externalities, pun not originally intended. But it turns out that that's the only thing that can go wrong. So, we found a couple of natural cases like the greedy algorithm, the M-greedy algorithm that do push through to approximately efficient investment. Footnote, I mentioned that the FP task does not. And we started trying to figure out like what's actually driving this. And the answer is precisely that these algorithms do not have these types of externalities. So we're running out of time, but let me say a little bit about this condition, state the positive result. Then I'm going to flash the proof on the screen. So if you want to pause the video and watch the proof, you can watch, and look through the proof. You can see it laid out in 2 slides. But we'll say that an algorithm excludes bossy negative externalities if either whenever you are packed and you raise your value, or you're not packed and you lower your value. So things that wouldn't change whether you get sort of included in the outcome. Any externality you have on the other bidders is positive. So if the value of a packed bidder is increased or the value of an unpacked bidder is reduced, the total value generated for the other bidders doesn't fall. This is precisely turning off this algorithmic externality I was talking about. And that gets you exactly the push through. So if X is monotone and exponent and is a beta approximation for allocation, then X is also going to be a beta approximation for investment. This tells us some things. For example, M greedy turns out to be a 1/2 approximation for investment, which is super cool. It also, I've stated this in this sort of unidimensional packed, unpacked case, but it extends to more complex allocation problems as well as combinatorial auctions under XOS valuations. And this exponent condition is sort of morally necessary. It's almost necessary in a precise sense. All right, so I promised I would flash the proof. It's 2 slides. It's actually stunningly quick, but I don't have time to go through all of the details in the talk today. So slide 1, slide 2, you can pause now. All right, and let's wrap up. So that is the result. If X is monotone and exponent, it's a beta approximation for allocation, then it's a beta approximation for investment. So you actually can characterize, and as I said, it's sort of an almost sharp characterization of when these investment guarantees push through, allocation guarantees push through to investment. there's lots of questions sort of to stack on top of that. We have some examples of exponent algorithms, but we don't have like sort of an exhaustive collection of examples. And we don't have sort of particularly good ways other than working through individual algorithms as yet to characterize them. Sort of would be really nice to know sort of like, for example, how restrictive is this condition? And can you sort of, take algorithms and find exponent neighbors, right? Is there a way to sort of, take any algorithm that has a good approximation guarantee for allocation and convert it into a version or a sort of an Oracle-based algorithm that would have a good approximation for investment? Also, we sort of don't know what the appropriate generalization for randomized algorithms looks like, although we're pretty sure that there would be one, right? There's sort of nothing in the argument that seems like it really depends directly on the fact that we're using, sort of deterministic algorithms. There's also, and this is a question that, we think about a lot as economists, right? Like what happens with price uncertainty, right? And that, a key to what's going on is that, bidders can optimize knowing their threshold price and expectation, right? They know what their equilibrium threshold price is going to be. If you don't have a clear sense of what your price is going to be, it's not totally clear how you choose your investments. It'd be good to know if that like introduces sort of additional distortion. In some other work, John Hatfield and Fujito Kojima and I show that in an additive approximation model that does in fact introduce a like very precise additional distortion. That was at EC a couple of years ago. But more broadly, and here's sort of like, if you're thinking about like a broader message for everyone who's tuning in at EC, one of the things we're excited about with this paper is it's sort of a way of thinking about the economic consequences of approximation, right? It's like we've done all this work to develop these really incredible approximation algorithms and then sort of convert them into, really useful mechanisms. This is an opportunity to say, okay, so what does that do in sort of like a broader, like, economic environment where now the participants have to invest in technology before they show up. And this is one way to ask a version of that question, but it's certainly not the only way to ask, like, what does approximation do sort of to participants' incentives in a broader system? So let me close there, QED, and looking forward to questions.